So we covered this lesson at the very end of last semester, so just in case we have any new students, I wanted to record a video going over how to, the introduction to the polynomial functions, where we spoke about degree, leading coefficient, end behavior, and roots. So firstly, let me just open a new page here, a new blank page. So a polynomial function comes in the form of ax to some power. For example, I'm just going to use 10 plus bx. This is where a and b are constants. X is our variable, to the 9th power, and so on, until we eventually get to some other term. So I believe it would wind up being h. I'm sorry, h. So it'd be ax to the 10th, bx to the 9th, plus cx to the 8th, plus dx to the 7th, and so on, where the exponents continue to decrease until we get hx to the 0, which is just h, so that's why we don't write that. But this is a polynomial function, and when you graph it, it'll have one of two types of end behavior. Either it will have end behavior that is different on both sides, meaning one graph goes up and one goes down. What happens in the middle will vary depending on exactly what the polynomial is. And the other type is where both ends of the polynomial graph go in the same direction. And again, what happens in the middle is kind of dependent on the polynomial itself, but we can know what the end behavior looks like. So yeah, this is end behavior. And these are dictated by the degree of the polynomial. So the degree is the largest exponent of a term in the polynomial function. Now, a polynomial function, the exponent has to be a positive integer, so it would have to be any whole number that's positive. So if it was a half or negative, you wouldn't consider that a polynomial function. But all polynomial functions will look like one of these two types of graphs. Either the end behaviors will be different, or they will be the same. They will be different in the case in which the leading coefficient's exponent is odd, so an odd degree polynomial. Whereas they will be the same in an even degree polynomial. So this example would fall into the category of having the same end behavior because it is even. So an even graph would be like x squared goes up on both sides, whereas x to the third would go from down to up. All right, there's one more thing that is important when it comes to determining what the end behaviors of the graph look like, and that is the leading coefficient. So that is the coefficient of the term that has the highest degree. So if the leading coefficient is any number but positive, it will have one of these two graphs. Whereas if the leading coefficient is negative, so this is a positive leading coefficient with an even degree. So positive leading coefficient with an even degree, whereas this would be a positive leading coefficient with a odd degree. If the leading coefficient is negative, such as negative 3x squared, the graph would have an end behavior that goes down on both sides, and then something would happen in the middle connecting the two ends. Whereas a negative odd degree, so let's say negative 5x to the 5th, would actually start by going up on the left and ending down on the right, and something would happen in the middle. So the negative graphs have the opposite end behavior. So a way to remember what the standard one it looks like is that you look at the right side of the graph and determine if it's going up. So if it's a positive graph, will be up on the right side. But for the negative graphs, the right side will be going down. So this would be the example of a odd degree, but a leading coefficient that is negative. Let me put the negative over here, I think. Whereas this would be an even degree with a negative leading coefficient. So let's take a look at an example. So I'm just going to make something up. So let's just say we had y equals negative 5x squared plus 2x to the 5th minus 5. This is a polynomial function. It's not currently written in standard form. So the first thing we're going to be doing is rewriting the equation in standard form. So y equals 2x to the 5th minus 5x squared minus 5. So the exponents are now in decreasing order. In this case, the polynomial would be 2x to the 5th plus 0x to the 4th plus 0x to the 3rd, and so on. But we're not going to write out the entire thing. But if we look at the leading coefficient, we can see that it is positive, and the exponent is odd. Therefore, the graph will go up on the right. It will have different end behavior. It will look something like this on a graph. The other thing that's important to know is that if a polynomial isn't currently multiplied out, that doesn't mean that you can't determine the end behavior. Here's another example. Let's say we had 3x, y equals 3x times x squared plus 2 times x minus 3. Now, we could multiply this out, and that might take time. If we just focus on all of the terms with the largest exponent in each individual factor, we have x to the first, we have an x to the second, and then x to the first. If we were to multiply these terms out, we will get a leading coefficient of 3x to the 4th power, which would give us an idea of what the graph looks like. Again, in this case, this is a positive leading coefficient with an even exponent. So that means it will go up on both ends, and what happens in the middle kind of varies. Lastly, the degree of the polynomial actually tells us a little bit about the roots of a polynomial. Let's take a look at one more example. So these are going to be several polynomials that are written in factored form. So this would be x plus 2, x plus 5, and x minus 3. This one, if we were to simplify that first term, it would become an x to the 3rd power, which would be useful for estimating what the graph looks like. But it also happens to have a root at x equals negative 2, because that would make this factor equal to 0. A root at x equals negative 5, because that would make this factor equal to 0. And the root at x equals 3, and that's because this factor equals to 0. So this polynomial, which is a 3rd degree polynomial, has 3 real roots. So if you were to look at the graph of this polynomial, it would actually have an x-intercept at negative 2, which is over here, negative 5, which is over here, and 3, which is over here. We'd see it's an odd degree with a positive leading coefficient, so it'll be up on the right. So the graph will look something like this. Now, it is possible that we get an equation that looks more like this, negative 2 x plus 3, x plus 3, and x minus 4. And this would be an example where the leading coefficient would eventually simplify to be negative 2x to the 3rd power, in which case this graph is a negative leading coefficient with an odd graph, so it would start up and it would go down on the right. It would have 2 x-intercepts. One would be at negative 3, because this is a repeated root. So they both have this root, and this would have a root at x equals 4. So at negative 3 and 4, there would be 2 roots. This one would look, so the graph would only intersect the x-axis in 2 places. There's one more example that's worth knowing about, and that is when we have imaginary roots. Now, imaginary roots occur when you have the polynomial factored. So let's factor as much as possible, but not all the factors can be factored more thoroughly than that. So for instance, if we had x times x squared plus 4 and x minus 3. This one can't be factored any further because it's the sum of squares. So x equals 0 would be the solution for this factor. X equals minus positive 3 would be the solution for this factor, or where the x-intercepts are on the graph. This one, we would have to set it equal to 0 and solve. We'd get x squared equals negative 4. And then when you take the square root of both sides, you have to put a plus and minus on this side. And we get the square root of negative 4 is 2i, as we should remember from last term. So that means, oh, whoops, I wrote a extra square here. I took the square root. There shouldn't be a square there. We get x equals 2i and x equals negative 2i. These are imaginary numbers and wouldn't appear on the graph. And if we were to multiply out the leading term for each of the factors, we would eventually get a x to the 4th power. So this graph would look something like this. It would have a root at 0, a root at 3. The other two roots we can ignore because they're not going to appear on the graph. The graph will be going up on the right, and because it's even, it has the same end behavior, and it will pass through those points like so. And that pretty much covers everything you need to know about the introduction to polynomial functions.